In the previous video, we learned about conjugated pi electron systems. Now, an important example of conjugated pi electron systems are dienes, in which the carbon-carbon double bonds are separated by a single bond. They are called conjugated dienes. In this video, we will look at the reactions of conjugated dienes. I have an equation here. We're mixing equal molar amounts of 1,3-butadiene and HBr. Note what's special about 1,3-butadiene is that it's an example of a conjugated diene. What is produced in this reaction? If you want to pause the video and figure it out on your own and write it on your scratch pad, that would be a good idea. What do you get? All right, well, let's take a look. Now, the thing that I've stressed is that when you see a double bond, think addition, notwithstanding the exceptions that we saw in the previous video. That is to say, if you have an allylic substrate, that's a leaving group and the carbon and the allylic carbon of an alkene, and you don't have an adding reagent, the reaction is likely to be a substitution, a replacement of that leaving group. The other reaction is if you have an alkene and the presence of one or more allylic hydrogens and an allylic halogenating agent, that will also not be addition, but rather an allylic substitution, an allylic halogenation. Well, here we have two double bonds in our reactant. We would probably want to apply the same general rule, think addition. All right. Here is one reasonable product. HBr adding across one of the double bonds. Now, to be consistent with the Markovnikov rule and all, we would want to attach it like so. So we would write for a product this. For emphasis, I'm putting in the hydrogen explicitly, one of them. It's a bond line drawing, basically, though. All right. So that would seem to be a reasonable response. What happens when you mix these two substances? Well, when you analyze the product, you find that yes, indeed, this product, this addition product forms. But there's a second product that forms as well. Let me write it. So if you wrote this, thinking on your own, you're right. Well, partially right. There's this other product that forms as well. And for emphasis, let me put in the hydrogen over here on the other end. Now, indeed, this second product, they form in comparable amounts, not exactly equal amounts. This is an addition product. Addition means two molecules unite to form a single molecule. But what's unusual about this second product is that the double bond has shifted one bond position to the middle two carbons, bromine attaching on one end of the 4-carbon chain and hydrogen on the other. How in the world can we explain that? indeed, when this was observed in the late 1800s, the formation of this second product was a surprise and initially baffled organic chemists. Let me, before I offer the explanation that chemists came up with in the late 1800s, let me mention the classification that we give to each of these products. The first addition product that I wrote, we can call the simple addition product. Simple addition. To cross one of the double bonds, the kind of the obvious one that you would expect. The less obvious one is called conjugate addition. So, simple addition. Conjugate addition. Now there's also an alternative way to distinguish between these two addition products. If we arbitrarily number the carbons of the conjugated diene, 1, 2, 3, 4, the first one is alternatively called 1,4 addition. I'm sorry, 1,2 addition, I misspoke. Addition. The conjugate addition is alternatively referred to as the 1,4 addition product. Because the hydrogen and bromine attach respectively in the simple addition to carbons 1 and 2, and then in the conjugate addition, H and Br attached respectively to carbons 1 and 4 in the original conjugated diene. Now, in 1899, the German chemist Thiele published what he called the theory of partial valency, and using this theory offered an explanation of how the conjugate addition product forms. This theory basically viewed the electrons of a conjugated diene as being mobile, that they can undergo displacement to meet the requirements of bonding. And interestingly, although the theory lacks the modern understanding of orbitals and bonding, that theory is not that far off. All right. Let me go to the PowerPoint slides and look at this idea of addition to conjugated dienes. All right. Okay. Here we are at the PowerPoint slides. The title of our discussion here, Addition to Conjugated Dienes. It's a general rule that when you have a conjugated diene and you mix with it an adding reagent, you'll get two addition products corresponding to what we showed before, a simple or 1,2 addition, and the second product, conjugate or 1,4 addition. Additions, you will recall in our discussion of alkenes, can be ionic or non-ionic. The non-ionic ones would include addition of hydrogen gas with catalyst to alkenes. With respect to addition to conjugated dienes, both with respect to ionic additions and non-ionic additions, we find that two products are correspondingly formed, a 1,2 addition and 1,4 addition. And let's see here. Yeah, here is an example of a non-ionic or non-polar addition. If you take 1,3-butadiene, mix with it hydrogen gas in the presence of catalysts like platinum, you get two addition products, one corresponding to hydrogen adding across, H2 molecule adding across the CC double bond, and the other corresponding to the 1,4 addition, where the double bond shifts over one place and apparently one hydrogen attaches to C carbon 1 and the other one on the opposite end to carbon 4. Here are some more examples of the addition to conjugated diene. I'm using, for simplicity, 1,3-butadiene in all cases. In these examples, these are all ionic additions. The one shown here corresponds to what I had in my drawing board. X is a halogen, so if you mix 1,3-butadiene and either HCl, HBr, or HI, stay away from HF, you get the two addition products, the 1,2 and 1,4 addition. If you mix a conjugated diene with a halogen, X is bromine, chlorine, or iodine, you also get the two addition products, 1,2 and 1,4, where apparently the halogen atoms attach across one of the double bonds, leaving the other alone. And then the conjugate addition, where one halogen attaches on carbon 1 and the other one on carbon 4, with the double bond migrating to one bond position, ending up between carbons 2 and 3. Here's another example. The acid catalyzed addition of water to a conjugated diene gives respectively this 1,2 addition product and this 1,4 addition product. Now, in terms of ionic addition, this pattern is followed. The adding reagent consists of two parts, an electrophile and nucleophile. You will always get two addition products, simple and conjugate. The electrophile attaches to C1 and the nucleophile attaches to C2, giving the simple addition, right? The conjugate addition, electrophile attaches at C1, the nucleophile on the opposite end at C4, and the double bond shifts over one bond. It's a general pattern that we see with respect to ionic addition. Now, what's the explanation of that? Well, let me preface it by this comment. There's a tendency now when you see the results to kind of think this way, to think, well, simple addition arises as I might expect in the given the usual mechanism that I've learned for addition to alkenes. But then I now have to come up with something totally different, a completely different pathway to explain the other result, that is the conjugate addition product. As I'll explain, though, the simple and the conjugate addition are outcomes of basically the same general pathway. And here we go. Using HX as an example, the HX is going to protonate an alkene carbon. Now, of course, there's two alkene carbons to choose from. It could protonate the CH2, the end one, or the one next door, the CH. Which one which one will occur? Which one's favored? Well, when the hydrogen ion attaches to the CH2, that produces a very stable allylic carbocation. I'm showing you here a single dotted line structure. If HX donated a proton to the CH carbon here, that would put the plus charge on the CH2. There wouldn't be any delocalization. That would be a very unstable primary carbocation, and that's the less likely result. When a reaction has a choice of forming two products, it will tend to form the more stable one as a general rule. So the hydrogen HX is going to protonate the CH2, giving the more stable two possible carbocations. Now this is, you recognize, an allylic carbocation. It is nature's most stable. I'm using a dotted line structure to show that. You could also alternatively show this with two resonance structures. Now, using the dotted line structure, the way it comes out is the plus charge is partly on this CH2 and the other on this CH. Right? So there are two carbons of the allylic carbon that bear a positive charge. The N carbon CH2 and the middle CH. Along comes the nucleophile here, X minus, and it feels an electrostatic attraction for either one. It feels a pull of a plus charge. Part of the time, the halide ion will feel the attraction of this plus CH, and when it does, it's going to push pi electrons over one bond position, and that's going to give you this product here. That it corresponds to simple addition. The other part of the time, halide ion feels the attraction of the plus charge on the CH2 when it bonds to that. That pushes pi electrons here over one bond position. So you end up with a double bond between carbons 2 and 3. Halide ion attaches on that CH2, and boom, there you've got your conjugate addition or 1,4 addition product being formed. In other words, the 1,2 and 1,4 addition products are two different outcomes of the allylic carbocation reacting, because it has positive charge on two different carbons, and the halide ion nucleophile part of the time attaches to one, giving one product, part of the time attaches to the other, giving the other product. Now, let me show you I'll go back to the drawing board and I'll show you an alternative way to think that through, which is consistent with the way I had set things up in our Part A discussion of Chapter 17. Okay, here I am at the whiteboard. I want to show you an alternative way to figure out the course of the reaction when a conjugated diene reacts with an adding reagent like HX. Okay, so HX is an acid. It's going to protonate the alkene, something we discussed previously. It's going to attach the proton to give the more stable allylic carbocation. So we'll be drawing our curved arrows, like so. All right, now let's draw the simplest carbocation that we can here. It is if we move the electron pair of the pi bond over to the H, that puts a plus charge on that carbon. Let's just draw that result. There we go. Now, okay, so that's the kind of the first simplest carbocation structure that one could draw on the drawing pad. But let's stop. One of the things that I encourage you to do is that when you have a structure, whether it's one that is given to you or you draw, stop and ask, can I draw resonance structures for that? And the answer is yes, you can. This would correspond to Roman numeral 1 type, and let's go ahead and draw the other resonance structure. Shifting the pi bond one bond position. And we're only shifting pi electrons. You're not changing the basic molecular framework at all. Okay, and plus charge on that carbon. All right, now those are the two resonance structures that we draw for this carbocation. This would be, I hope you all see, an allylic carbocation. Well, The byproduct of that, of course, is the halide ion, and that's going to act as a nucleophile. Okay, now what we're going to do next is similar to what we did in the part A. We realize that resonance structures are not real, they're drawings. The real molecule is a blend or a composite of those. Here on our drawing board, we're going to pretend that each one's real, and we're going to take each one respectively to its logical product. So let's look at the first carbocation. I know you're not real, but I'm going to pretend that you're real, and I take the halide ion, nucleophilically bond it to the plus carbon. No, don't change anything else. That's going to give this. And we see that corresponds to the 1,2 addition product. Okay. Now, do the same thing on the other resonance structure. I know you're not real, but I'm going to pretend that you are. And I'll take the halide ion as a nucleophile and just simply form a bond between the nucleophile and that plus carbon. Draw the result of that. And there you go. This corresponds to our 1,4 addition product. So the idea here is that it isn't a case of, well, you get two products. One of them forms by some kind of a straightforward, simple way, and the other by a more complex way. The two products form because it's single allylic carbocation reacting with the nucleophile two different ways to give respectively two different products. And this general mechanism is followed for all of the ionic type addition reactions. Okay. Okay. Now, one important issue to address is this. We know that that two products form when a conjugate diene undergoes addition. One product called 1,2 addition, the other called 1,4 addition product. What about the relative amounts? I mentioned it briefly before. They are formed in comparable amounts. The percentages of each varies, however. What does it depend on? You might be surprised to learn that the main variable controlling the percentages of 1,2 and 1,4 addition product to form is the temperature. Temperature is the key to determining which is the major product, which is the minor product. And we illustrate that with this example. I take 1,3-butadiene and HBr. If you go to a low temperature, minus 80 degrees, that's achieved by a dry ice acetone bath. You get your two products, 1,2 and 1,4 addition. The major product is the 1,2 addition product. 80% of the product is that. 1,4 addition is a minor. It's formed in 20% amount. Now, if you redo the reaction at a higher temperature, 40 degrees, now that's not a high temperature, but it is 120 degrees higher than before, a big difference in temperature. You get the same two products, but the percentages change. At the higher 40 degrees Celsius temperature, now The 1,4 addition product is the major product. It forms in 80%. The 1,2 addition forms in 20%. All right, what's going on? To explain that, go to the next slide. I'm going to explain it by drawing an energy profile. Now, in an energy profile, we graph the energy of the reaction, usually the potential energy, versus the progress of reaction. Now, ordinarily in an energy profile, we have the reactants on the left, and we proceed to the right to get the products, from reactants to products going from left to right. Here I'm going to do it a little differently. For the reactant, I'm not starting with the conjugated diene, I'm starting with the allylic carbocation that formed. Now remember, the allylic carbocation is the precursor of two products, the 1,2 addition and the 1,4 addition product, respectively. Now, in my energy profile, I'm going to take the energy of the allylic carbocation and plus halide ion. That's what this energy mark here represents. I'm going to show two energy hills, one which gives the 1,2 addition product, and the other gives the 1,4 addition product. Well, let's see what's going on here. Notice down here on the left, this product here is the 1,2 addition product. So if I start in the middle here and go from right to left, I go over this energy hill, and I form the 1,2 addition product. All right. To get the 1,4 addition product, I go from left to right over this energy hill, and I get then the 1,4 addition product. Now, first thing to think about is which product is going to form faster and why? Well, look carefully at the dotted line structure that I've drawn here. Recall that the +1 charge, a fraction is on the end carbon, a fraction in the middle carbon. It turns out, and I think you'll agree this makes sense, that the larger fraction of the positive charge resides on this middle carbon, the smaller fraction on the end carbon. Why? Well, the middle carbon is a secondary carbon. A positive charge is more stable in it. So a greater amount of positive charge would be accommodated on that middle carbon. The CH2 is primary and it doesn't like to have a positive charge. Only a smaller share of the positive charge would be on that primary CH2 carbon. It's, let's see, I don't recall, it's something like, it might be a +0.8 charge on this middle carbon and +0.2 on this carbon. All right. Now the halide ion is going to attack respectively the middle positive carbon or the end positive carbon. Which one's easier and faster? Well, obviously electrostatically the halide ion has a greater attraction for the carbon that has greater positive charge, and so it's going to form a bond more easily to that. The halide ion attaching to this gives the 1,2 addition product. That would correspond to going over this energy hill. The halide ion attaching to the other carbon, well, that's a harder process because the positive charge is not as great, and it's going to have to work harder to form a bond there. So you see, in other words, what I'm explaining is halide ion bonding to this middle positive carbon to give the 1,2 product. That's easier and a faster process than attaching to the end carbon that gives the 1,4. Now, an easier and faster process would have a lower energy of activation. That is, the transition state here is lower. That's for the 1,2 addition product being formed. Is lower than the transition state for the 1,4. All right. Now, at low temperature, it seems to be guided by this. The product that's going to form favorably is the one that forms easier and faster at low temperature. So at low temperature, it's going to be easier to form the 1,2 addition product, and so you're going to get more product from that pathway than you will the other one. More times the allylic cation will attach the halide ion with the energy hill, with the lower energy hill, more often than it will to climb the higher energy hill. So at lower temperature, the major product is the formation of the 1,2 addition product. The one that forms faster than the other. Now, at low temperature, this. Molecules don't have a lot of kinetic energy. The products that form have such a low kinetic energy, once they form, they don't do much else, they just sit there. If they had higher kinetic energy, they might want to react and climb the hill backwards. You know, reactions can do that. Reactions can go over an energy hill, forward and reverse. But at low temperature, things are just, pretty sluggish and low-key and lazy. And once they form, they're done. They're not going to do much else. They don't have the energy to do much else. However, things change when you go to higher temperature. At higher temperature, the products that form do have enough kinetic energy to make that climb backwards over the energy pathway. The 1,2 addition reaction can react in reverse, climbing backwards to reform the allylic cation and halide ion, and also the 1,4 can make that climb backward to reform the allylic cation and halide ion. Now, in a reaction where you have things going in both forward and reverse direction in the pathway, you realize what's going to happen. When you have a reaction where the reaction proceeds in both directions, as it would here as I explain at high temperature, what's going to ultimately happen is equilibrium is going to be reached. That's the key. At high temperature, where you have reversal of the reaction occurring, the products that form will come into equilibrium. That's just the law of nature. When there is both forward and reverse processes, you will get equilibrium. Now, when two things are in equilibrium, there's another law of nature that kicks in. Regardless of how they got there, the more stable one, if two things are in equilibrium, the more stable one always predominates. It's just a simple law of nature. When two things are in equilibrium, the more stable, the lower energy one will always predominate. The greater the difference in energy, then the greater the difference in the relative amounts. Well, okay, so here you go. At high temperature, when reversal occurs and equilibrium sets in, the major product that forms is the one that's more stable, right? The more stable one predominates. Well, which is more stable, a 1,2 or 1,4? Okay, you can answer this if you think back to what we learned in chapter 8, I guess it is. We talked about alkenes and alkene stability. An alkene is more stable the more alkyl groups attached. If you look at the 1,2 addition product, there's just one alkyl group attached here, just one. Whereas the 1,4 has two alkyl groups attached. All right, one on one end, one on the other. The 1,4 addition, because it has two alkyl groups, is going to be more stable, have lower energy, and you can see that now in the energy diagram that I've drawn for this, in the energy profile. The energy mark for the 1,4 addition product you see here is lower energy than the energy mark for the 1,2 addition product. 1,2 addition, more stable, has lower energy. At higher temperature, when the two products are coming into equilibrium, 1,4 addition is more stable, lower energy, and will predominate. That's why at higher temperature, the major product is 1,4. At low temperature, when the reaction is controlled by the one that forms faster, it predominates. The predominant product is 1,2 addition because it forms faster than 1,4. But at higher temperature, when equilibrium sets in, the major product is determined by the one that's more stable. Now, the chemists have come up with an elegant way to distinguish between those two, and it's this. At low temperature, they say that the reaction is kinetically controlled. Kinetic means that the one that forms faster predominates. At low temperature, the reaction is kinetically controlled. 1,2 addition predominates because 1,2 addition forms faster. At higher temperature, the reaction is equilibrium controlled, or some say thermodynamically controlled. The product that dominates is the more stable product, not necessarily the one that forms faster, but the one that is more stable. And in a nutshell, that's going to govern the relative amounts of 1,2 and 1,4 addition product or an ionic addition across the board, regardless of whether it's adding acid catalyzed addition of water, whether you're adding halogen, whether you're adding HF, and so forth. It's the temperature that determines which product will predominate. Low temperature, it's kinetically controlled. High temperature, it's equilibrium controlled. Oh, let me back up and explain one other little bit of icing on the cake, so to speak. Suppose this is the reaction of 1,2-butadiene HBr. Go to that low temperature, -80 degrees. We know, of course, that 1,214, 1,2 addition is predominant 80% versus 1,4, 20%. Now let's let the reaction completely, so that there's no, when the reaction is complete, there's no longer any HBr there, no longer any butadiene. Right? We add the amount so that will happen. So at low temperature, we're sitting there with everything converted to the product mixture. 80% of it is 1,2, 20% is 1,4. However, let's do this. Let's take that product mixture and just warm it up. Just warm it up from -80 to 40 degrees. Right, and let it sit there for a few hours. Bring it up to 40 and let it sit for a few hours, and go back and analyze the product mixture. Guess what you'll find? That the percentages have changed, and the percentages are in line with that at higher temperature, 1,4 addition is a predominant product. If we take the original cold product mixture and warm it up to 40 degrees, the composition will in fact correspond to 1,4 being the major product, 80%, and 1,2 being the minor product, 20%.